Looks like here we've got this square structure of atoms of two different types. So we've got type A atoms on this diagonal and type B atoms on the other diagonal. And we've got the epsilon values for both the AA bond and the BB bond and the combination AB bond. And we want to figure out presumably the exact bond energy here, taking into account all possible bonds. So what are some bonds we should include here?
We have the AB and then the AA and BB.
Yeah. So starting with the AB bonds, how many copies of that do we have?
We have 4.
Yeah, looks like we've got 4 copies of an AB bond. 1, 2, 3, 4. And those are all equilibrium distance from each other. So we got 4 copies of AB. I guess we could call those nearest neighbor or just equilibrium distance bonds. At a cost or value of what would be the energy for each one of those? What would be if we want to find, we're trying to find the bond energy. What is the bond energy of one bond?
The potential energy associated with their distance.
Yeah, and in this case, their distance is equilibrium because we assume these adjacent atoms are at equilibrium distance from each other. So what's the potential energy at equilibrium?
The well depth.
Right, in other words, epsilon. So in general, anytime you've got atoms that are at equilibrium distance from each other, you should assume their potential energy is -1 epsilon. And the actual value of epsilon depends on the type of atom. In this case, we're talking about an atom A and atom B linked together. So we use epsilon AB. So we'd have negative epsilon AB each. Oh, I can't copy paste from this. Let me go grab an epsilon from elsewhere. Epsilon, there's one. Okay, negative epsilon AB each. So each one of those bonds has negative epsilon AB as its energy, and we have a value for that, but we can plug that in at the end for a total of -4 epsilon AB. So that would be the energy of those 4 bonds. And that's most of the bond energy right there. But what other bonds do we still need to account for?
The AA and BB.
Yeah, we've got a bond from AA. It looks like just one. And we've also got one bond from B to B. So we also have, listing all those out, we've got one copy of an AA bond. And is that equilibrium distance?
That would be R0 rad 2.
Yeah. And so for the value there, it's going to be somewhat weaker than epsilon. So what would be how could we get a value for that? If we know the distance is √2 times R0, how could we get a value for energy associated with that?
Could we use the formula?
Yeah, you could use the equation for energy. And what's that going to be?
I don't remember it off the top of my head, but it's something like sigma over something to the 12th minus.
Yeah. So we could use that formula, or we could use the Lennard-Jones potential energy graph. But either way, you get a value for energy. And that'll end up just being some fraction of epsilon. So some negative fraction of epsilon, specifically epsilon AA. So we're going to have some fraction of epsilon negative some fraction of epsilon AA each, but there's only one of them, so that is the value of that one bond. And again, you can get that fraction by looking it up on either the graph or plugging this distance into an equation. And for that distance, what is R naught in terms of sigma? Because most of the graphs and equations are in terms of sigma. Like, what is the usual equilibrium distance?
1.112 sigma.
Yeah, so 1.12 times square root of 2 sigma. And square root of 2 is about 1.414. So 1.12 times 1.414 sigma should be the distance you're looking for. Either plug that value into the equation for energy at a distance or look it up on the graph. Either way, it should get you a pretty good approximation. I mean, the equation gets you the exact value. The graph will get you a pretty close estimate, depending on how accurate the graph is. And that'll give you some fraction of epsilon. And then for the BB bond, you can do the same thing. Looks like we have one copy of the BB bond. And that's the same distance. It's the same diagonal in this square. So we also have 1.12 times 1.414 sigma as the distance. And that will be at a value of, or the energy value will be that same fraction of epsilon BB instead. So in this case, we'll have that same fraction, but for epsilon BB instead. So that'll tell us the energies involved. We've got, what do we have here? So we've got this much energy from the bonds along the sides of the square, plus also this much energy from that one AA diagonal, and this much energy from that one BB diagonal. And then what would you do with those values?
You would just add them together.
Yeah, add those together. And you would then be also plugging in these specific values. The 20 times 10 to the negative 21 for AA, 5 times 10 to the negative 21 for BB, and 3 times 10 to the negative 21 for AB. And that should tell you the actual bond energy of this entire structure. Any other questions on that?
But if we just directly use the formula, then we're already accounting for the epsilon.
The formula should have epsilon in it, right? It's like something over r to the 12th and something over r to the 6th times epsilon.
Yeah.
Yeah. So that would be, you'd specifically use the epsilon relevant to those atoms.
Okay.
But the main purpose of that is getting the fraction of epsilon that you care about there. Because epsilon is basically just what we're using as the unit of measurement for energy. But the actual value of epsilon is going to be one of these values depending on the atoms involved.
Okay.
Any other questions on that so far? Or any other questions on the bond energy of this structure in general?
If the atoms were different sizes, like B was larger than A, how would that change how we would solve the problem?
In that case, the distances would be different. And I think that would involve some more complicated geometry because you'd have to figure out, like, let's say B was larger, as we said. Then we'd have something like, let's say, the B atom here and here. And then the A atom maybe like here and here. So in that case, you would need to know more information about how they're structured, because they're certainly not going to be a square. And I think the thing is exactly how they're structured is largely going to depend on which bonds are weaker versus stronger, I think. Because for instance, if the A atoms are a very strong bond, then they're going to be attracting each other, and the B atoms are going to get shoved further out. So maybe something more like this. Whereas if the BB bond is stronger and the AA bond is weaker, then the B atoms would get attracted close to each other and the A atoms would be pushed further out by that. So it might look like this instead. So I think in that case, you really would need to know more information. It's not just going to form a nice, neat square. Any other questions on that? All right, then let's take a look at the idea of modes and the thermal energy stuff. Because what we've been looking at so far is all of the bond energy, looking at just what's going on at the bottom of that energy well. But the thing is, if you, there we go. Can you see the new blank screen? Okay, so let's say we take a look at that usual Lennard-Jones potential graph. And here, let's assume for the moment we're looking at just a single pair of particles. So we have our usual graph for potential energy. That didn't work so well. Let's see. Something like that. I guess it should be more here. All right, so our graph of potential energy for the pair of particles. And let's say we put the total energy very low. In fact, let's say we put total energy all the way at the bottom here. So we've got potential energy, we've got total energy. And in that case, what would the kinetic energy graph look like if your E total is all the way down at negative epsilon? How would you actually draw out the kinetic energy graph in this case? Usually you want to start by looking for any locations where kinetic energy is zero. And how would you find that? How would you find a location where the kinetic energy has to be zero?
When the PE is equal to E total.
Yeah, and it looks like we do have one point where that happens at that very bottom there. So at this R value, the R value of equilibrium, we're going to have one location where kinetic energy is zero. And then if we take a look to the right or to the left, if you go to the right, potential energy is increasing, so kinetic energy would have to decrease. But why wouldn't we actually draw that out?
Sorry, can you repeat that question?
If we start from equilibrium and go to the right, potential energy is increasing, right?
Yeah.
So we should expect kinetic energy to decrease as we go to the right. But why would we not actually include that on the graph here?
Because KE can't be a negative value.
Right, so we've got to ignore that and just say it can't go to the right. The particles do not have enough energy to move to the right. And same thing to the left. If we were to go to the left, potential energy would increase, so kinetic energy would decrease. But again, kinetic energy can't be negative. So the entire kinetic energy graph then is just this one point. This is the lowest energy the system can possibly have. This represents a pair of particles where the total energy is all the way down at negative epsilon. And how have you described the behavior of these particles? What are they doing?
They're not moving.
Right, these are two particles that are not moving at all. They're just at equilibrium distance from each other and at rest, no, not even vibrating. because the kinetic energy is 0, and this is the only legal location for the particles. They can't be anywhere else. So this describes a system where the two particles are at equilibrium distance from each other and at rest forever. And how would you describe that more macroscopically? If you had a system of lots and lots of molecules that were in this situation, just at rest at equilibrium from each other, how would you describe that macroscopically? If the atoms are not even vibrating. What would you be able to observe about the system? Because you're not looking at this with some tiny microscope. They are definitely solid, but the thing is, solid just means they're bonded together. This is even more so than solid. This is not only that they're bonded, but they are the lowest possible energy, and the molecules are not even vibrating. So if the molecules are not even vibrating, what temperature would you have here? Yeah, this represents absolute 0, because temperature is really all about the oscillations of the particles themselves. If the particles are not oscillating, your temperature is true 0 kelvins. So this represents a system with no thermal energy whatsoever. It has bond energy. Its bond energy would be -1 epsilon, but the thermal energy would be nothing. So let's try describing this system. We can say this system has, as just a description of the system, we have bond energy is -1 epsilon. Thermal energy is 0. And note that the bond energy in this case is the same as the potential energy. The potential energy is negative epsilon, and so is the bond energy. And we have no thermal energy at all. But let's try adding some energy. Let's say we raise total energy by some amount. First, let me put a mark at where total energy was. Here's our negative epsilon mark. Let's say we now raise E total up to some new amount. Let's say we add some heat to the system, we increase E total up to some new value. That is, let's say, negative epsilon plus delta E, plus delta E. So delta E is the amount of energy we've added. Or let's actually call that heat, because presumably we are adding heat to the system. In that case, what is that going to change for the kinetic energy graph? Yeah, the kinetic energy is going to increase. In fact, it should also increase by, or we're basically taking that graph and raising it by plus Q. So let's draw our new kinetic energy graph. First of all, we can start by drawing out the 0 points as before. We look for locations where potential energy meets E total. So here's a location where kinetic energy is the same as E total, so that's going to be no kinetic energy. Here's a location where potential energy meets E total, so that location has no kinetic energy. So there are still some locations where kinetic energy would be 0. But there's a region in between where potential energy is less than E total, so there is some energy available for kinetic energy. Specifically, as potential energy decreases, kinetic energy is going to increase above 0, so that's okay. Potential energy levels off to a minimum, so kinetic energy is going to level off to a maximum. And what will that maximum be? What will be the highest kinetic energy that's available here? How do you usually calculate the kinetic energy on a graph like this? Yeah, we take E total minus the potential energy. In other words, the difference. Specifically, the difference between E total and potential energy. That difference is the value of kinetic energy. And you could do that at any location. You could say that at a certain R value, this difference between E total and potential energy is the kinetic energy at that location. Or this difference between E total and potential energy, that value, that distance is the kinetic energy at that location. So let's try this. We could actually move these differences up to the axis. And these differences should tell us the value of kinetic energy at each of these locations. So that should be something like this. So there's our kinetic energy graph. And what would be the actual value of the highest kinetic energy? If you actually calculate that using kinetic energy equals E total minus potential energy, what's E total here? Yeah, we've got this negative epsilon plus Q. And then when we want to subtract the potential energy, specifically the potential energy at equilibrium, which is what value?
Epsilon.
Yeah, or negative epsilon since it's below the axis. So when we subtract those, negative epsilon minus negative epsilon cancels out, we're left with just Q. In other words, the heat we added is now the maximum kinetic energy. So we've really changed both of these. We've raised E total, that changes the kinetic energy graph. So kinetic energy now ranges from 0 all the way up to Q. And potential energy, instead of being stuck at negative epsilon, potential energy now ranges from negative epsilon up to negative epsilon plus Q. So the heat we've added, we wouldn't really say the heat we've added all went into kinetic energy. The heat we've added goes into increasing the options for kinetic energy and also increasing the options for potential energy. Because as the particles oscillate, which they are now doing, kinetic energy could be anywhere between 0 up to Q. And potential energy can be anywhere between negative epsilon up to negative epsilon plus Q. And on average, they're going to be about halfway between. The particles are spending some of their time moving fast and some of their time being far apart or close together, but most of their time being somewhere in between. So we can say the average kinetic energy is going to be halfway between those. Average KE is going to be halfway between 0 and Q, in other words, Q over 2. And the average potential energy is going to be halfway between these, halfway between negative epsilon and negative epsilon plus Q. In other words, negative epsilon plus Q over 2. So we've raised the average kinetic energy from 0 to Q over 2, half the energy we've added. We've raised the average potential energy from 0 up to halfway to the E total, negative epsilon plus Q over 2. In other words, half the energy we added went into kinetic energy on average, and half the energy we added went into potential energy on average. Any questions on that so far? So let's see what the system now looks like. For the new values, has E-bond changed? Have we actually broken any bonds? Have we changed phase here? No, it started off bonded, it's still bonded. So we can say E-bond has not changed, it's still negative epsilon. Which means all the energy we added went into E thermal. E thermal is the original value plus the heat we added. In other words, E thermal is Q. So that means the average kinetic energy is half the thermal energy, and the average potential energy, at least the amount we added, is half the thermal energy. So let's make those substitutions. Average kinetic energy is half the thermal energy. Average potential energy is negative epsilon, which was the bond energy and still is, plus half the thermal energy. So this is how that breaks down. You can split this up into thermal energy and bond energy as the total energy of the system. Or you could think of the total energy as split into kinetic energy and potential energy of the individual molecules. But it's really the same thing. The potential energy and kinetic energy of the molecules are the thermal energy and bond energy of the whole system. It's just two different ways of splitting up total energy. Any questions on that so far?
Why is bond energy defined when the system is at temperature 0 Kelvin?
It's not so much defined as when the temperature is 0. It's more that the bond energy doesn't change unless the phase changes. So bond energy is the sort of a baseline. Bond energy is this negative epsilon of the bond itself. The extra energy we added in is considered thermal energy. So I guess you could say that the bond energy, if I may just draw some arrows here, the bond energy is this much. The bond energy is the energy of the bond itself, which is negative epsilon. The thermal energy is the extra energy we add above, or assuming it started off at absolute 0, because that's what we're defining everything from in terms of a reference point. Thermal energy is the extra energy it has above and beyond that. So you could say thermal energy is this quantity. Bond energy is this negative epsilon it has because the particles are bonded. Thermal energy is the extra energy it has above that baseline level. And then if you add those, you get the total energy, which in this case would be negative epsilon plus the heat we added from absolute 0. Any other questions on that so far? And one very useful way to think of this in terms of actually piecing this all together, like I said, we can split up the total energy into thermal energy and bond energy of the whole system, or we can imagine splitting it up into kinetic energy and potential energy of the individual molecules. So let me try drawing out a diagram that I think will help with that. If we treat this box as representing the total energy of the whole system, you could think of that energy as split up into the kinetic energy and potential energy of the individual molecules, because the molecules themselves have kinetic energy and potential energy. So let's say we split that up. We have, let's say we've got the kinetic energy. Actually, let me use the same colors here. We've got the kinetic energy of the individual molecules. And we've also got the potential energy of the individual molecules. And together they add up to E total. But you could also split up the E total by thinking of it in terms of potential energy, or sorry, the thermal energy and bond energy. And the bond energy, notice that the potential energy consists, when we write it out as addition like this, the average potential energy consists of the bond energy plus half the thermal energy. Because all the bond energy counts as potential, but the thermal energy we added, the extra plus Q heat, some of that goes into making the molecules move faster. Some of it goes into making the molecules able to be close together or far apart. And on average, half the energy we added as thermal energy counts as kinetic, and the other half of the thermal energy counts as potential. So if we wanted to split this up instead as thermal energy and bond energy, we could say the bond energy is sum of the potential energy. So sum of the potential energy counts as bond energy. So let's say this section is E-bond. But the rest of the potential energy and all the kinetic energy count as thermal energy. So all this would count as thermal energy. So this is how I usually think of this, that you can split up the E total as kinetic energy and potential energy of the molecules, or you could split up E total as the thermal energy of the whole system, which includes all the kinetic and some of the potential, and the bond energy of the system, which is the rest of the potential. So that E bond is the negative epsilon part of potential. The rest of the potential is the plus half the thermal energy. And then the kinetic energy is the other half of the thermal energy. Any questions on that so far? The split up of the energies? So this means that the thermal energy includes both kinetic and potential energy. The bond energy is just the potential energy at the baseline because the particles are bonded. The thermal energy is about how much extra energy the molecules have to be able to vibrate. And as they vibrate, they've got kinetic energy because they're in motion, and they've got extra potential energy because they're able to get close together and far apart. And we generally describe this extra energy in terms of the idea of modes. Modes is all about how the thermal energy is split up. Modes, or degrees of freedom, they're sometimes called. A mode or a degree of freedom is just a way to have energy. A way for a particle to have energy. Specifically thermal energy, but that thermal energy, again, is split up into both kinetic and potential. That the kinetic energy that the particles have because they can move, and the extra potential energy that allows them to be closer together or further apart, that all counts as thermal energy. And we usually specify a mode as an independent way for a particle to have thermal energy. And independent is a mathematical term here that can basically be thought of as at right angles to each other, perpendicular, that we don't want any accidental overlap by saying things are kind of in the same direction and sort of overlap. We're looking specifically at perpendicular directions here. So if the particles can have thermal energy that counts as kinetic and potential, they've got kinetic energy because they're able to move. And how many dimensions are they able to move in? Yeah, they can move in 3 dimensions. Any given particle, even if it's in a solid form, even if it's bonded and surrounded by other molecules, is able to vibrate in 3 dimensions, forward and backward, left and right, up and down. So that means that we say it has 3 translational modes. Three translational modes, because it's able to move in 3 dimensions. Those count as kinetic energy. And also, it's able to interact with its neighbors in 3 dimensions. It's able to interact with particles to the left and right, above and below, and in front and behind. So that means it has 3, and these are sometimes called external vibrational modes, which count as potential energy. And sometimes these are all lumped together and we just say the particle has 6 vibrational modes, of which 3 are kinetic and 3 are potential. 6 vibrational modes. So I've seen this described in both of these ways. You could say that the particle, one individual particle has 3 translational modes because it's able to move in 3 dimensions, and 3 external vibrational modes. External in the sense that this particle is vibrating with other particles nearby. Or you could just say it has 6 vibrational modes, of which 3 count as kinetic energy and 3 count as potential energy. And note that this also goes back to the idea that as we account for the thermal energy, half of that thermal energy is potential energy, and the other half of the thermal energy is kinetic energy. Because half of it goes into the 3 kinetic energy modes, and the other half goes into the 3 potential energy modes. One of the really big important ideas of modes is we expect energy to be distributed equally to all the modes. If you're adding some energy to the system, we should expect that each mode gets the same share of that energy. Unless, are there any situations where you would expect modes to not have the same energy as each other? Like maybe one molecule has way more energy than another molecule.
Could it be if they like differ in size?
Sorry, different what?
Like if the 2 molecules are different sizes?
The size isn't really the important thing though, because it's entirely possible for 2 things of different sizes to have the same energy as each other. But this is ultimately talking about thermal energy, right? What's the indicator for thermal energy?
The temperature.
Right, temperature. So if a substance has patches at different temperatures, like let's say this region is hot and this region is cold, then the hot region is going to have molecules with more energy per mode, and the cold region is going to have molecules with less energy per mode. In fact, temperature is really what the energy per mode is all about. Or we could even say that the other way around. We could say that temperature is just measuring the energy per mode. But this idea that if everything's at the same temperature, then energy is evenly distributed to all the modes, this is really the key idea behind pretty much all of thermodynamics. And this is typically called the equipartition theorem. Equipartition in the sense of equally split up, equal shares to all the modes. And this just says if a system is at thermal equilibrium, in other words, everything's at the same temperature, then the thermal energy is equally distributed to all of the available modes. And we specify available modes because it might be the case that some modes cannot be or cannot happen at the moment. Specifically at very low temperatures, sometimes some modes don't activate, or some modes might not be possible in the current state of the system. We also specify usually on average here, because this is an ongoing process. As the molecules vibrate around, maybe at some instant in time, one of them is moving faster than its neighbors, or one of them is closer to its neighbors than some of the other ones are elsewhere. So kinetic and potential energy of an individual molecule are in a constant state of oscillation. But on average, we should expect each mode to have about the same amount of energy because there's no reason to expect one of them to have more or less energy than all of the others. So overall, the energy per mode only depends on the temperature. It doesn't matter if the molecules are near each other or far from each other. It doesn't matter how large they are or what type of molecule they are. The only thing that matters for how much energy a mode has is the temperature. Energy per mode depends only on temperature, which means we can write energy per mode. Energy of one mode is something times the temperature. And that something is just a constant called half of Boltzmann's constant. Boltzmann's constant over 2. Where Boltzmann's constant is a universal constant. I forget exactly what it was, but it's going to be measured in joules per Kelvin, and it's extremely small because we're talking about energy of individual molecules here. But this is typically how you would calculate the energy in one mode. If you know the temperature of the system, you can take that temperature, which has to be in Kelvin because it's temperature, not delta temperature, multiply by half of Boltzmann's constant, and that tells you the energy of one mode in the system, one mode of any molecule in that system. Doesn't matter which molecule, doesn't matter which type of mode, whether it's kinetic or potential, one mode has this much energy, kb over 2 times the temperature. And like I said, you could think of this as basically what temperature means. Temperature is a description of how much energy each mode has on average. Any questions on that so far? And then if you want to look at the whole molecule, let's say you are talking about one molecule. If you want to find the thermal energy of the whole molecule, we know each mode has temperature times Boltzmann's constant over 2. A mixed phase, different phases could have different numbers of modes. The idea of 3 translational modes and 3 vibrational modes works very well for solids. It's a reasonable approximation for liquids, though liquids can kind of be more complicated. For gases, though, things change. Because if you're talking about molecules in a gas, what do you know about the behavior of molecules in a gas? How much are the molecules interacting with each other? Yeah, it should have just kinetic energy. There is one way it can have potential energy as well, but it doesn't have potential energy with neighboring molecules because there are no neighboring molecules. In a gas, we assume the particles are very far apart and not interacting with each other at all. So in a gas, you'd still have the 3 translational modes because the molecules are able to move in 3 dimensions, but you would not have the external vibrational modes because the molecules are not interacting with each other. There are other types of modes it could have, though. For instance, if you take a look at a molecule that's not just a single atom, like let's say you're dealing with, let's say N2, nitrogen. If you've got a nitrogen molecule, with this nice neat triple bond here, in a nitrogen molecule, and let's say this is a gas, the particle is able to move around. So it's got the 3 translational modes. Which count as kinetic energy. But it's not only able to move around in space. What other ways could it move? Or what other ways could it have energy? In addition to just moving around in space, how else could this particle have energy? Yeah, it could have rotational energy. This particle is basically shaped like a line, so it could be spinning. If you've got this object spinning, it would have rotational modes, rotational kinetic energy, because rotation also counts as a motion in terms of kinetic energy. It's not translational motion, it's rotational motion, but that still involves kinetic energy. And how many dimensions can it rotate in? We are in a 3-dimensional universe, yeah. The problem is that based on the shape of this object, this diatomic molecule is linear in shape. So if we take a look at the ways it can rotate, let's say you rotate around this axis. If you spin around this axis, that is a meaningful rotation. If you spin around this axis, that is a meaningful rotation. But if you spin around this axis, nothing's really changing if I spin it like this. So if you rotate a linear object around its own axis of symmetry, nothing's really happening. That does not count as a meaningful axis of rotation. So this linearly shaped molecule only has 2 rotational modes. And that's generally true for any molecule where all the atoms are arranged in a straight line. In any linear molecule, it only has 2 rotational modes. If it was nonlinear, though, like water, for instance, you've got oxygen atom, hydrogen atom, at angles like this, and there's a bend in it. So for the water molecule, this is nonlinear in shape, so it would have 3 rotational modes in addition to the 3 translational modes. So let's assuming it's a gas, for example. So generally, any diatomic gas, and not just diatomic, any gas where the molecules are linear in shape are going to have 2 rotational modes because there's 2 ways for it to rotate. If it's nonlinear in shape, it's going to have 3 rotational modes. And also within the molecule, the individual atoms could be vibrating back and forth against each other along the molecular bond. So you could have vibration inside the molecule, and that counts as kinetic and potential energy. So we would call this the internal vibrational modes. And that counts, that encompasses both kinetic and potential energy of the molecules vibrating against each other. However, this bond is only one-dimensional. If you've got a diatomic molecule, the atoms within that molecule can vibrate against each other along that one bond. It acts like one tiny invisible spring. They're not really rotating, or if they're vibrating like up and down, that's really more of a rotation. If they're both moving to the side, that's more of a translation. But there's one way they could be oscillating in and out. So we have one kinetic energy mode and one potential energy mode associated with that vibration. So that would be two internal vibrational modes. So this molecule, we could expect to have 7 modes if all these modes are active. In practice, they're not always all going to be active. In a gas, the molecules can always move, so you're always going to have the 3 translational modes. If you're not extremely cold, they'll also be able to rotate. At very low temperatures, it's too cold. There's not enough energy for them to rotate. So you'd only have the 3 translational modes. But once you get to around room temperature, there's enough energy for them to rotate, so you'd have 5 total. And if you get to much hotter temperatures, they're also able to vibrate internally, so you'd have all 7 modes. But at colder temperatures, some of these modes might be frozen out, we would describe it as. We would say the modes are frozen out, meaning there's not enough energy for them to activate. And that's why we have to specify all of the available modes in the equipartition theorem. Some of the modes might be frozen out at low temperatures because there's not enough energy. But that's the main idea here, being able to count up how many modes of what type. And then let's say all 7 are active. The energy of this one molecule would be 7 times 1/2 kb times temperature. Because each one of these modes has kb over 2 times temperature as the energy. Multiply that energy per mode times number of modes in the molecule, and that tells you the energy of that molecule. If you're looking for just one type of energy, like let's say you want to know how fast this molecule is moving, what are the only modes you would care about if what you want to find is how fast it's moving? Yeah, and specifically just the translational kinetic energy, because rotational kinetic energy is more about how fast it's spinning. So if all you care about is how fast the molecule is moving, look at just the 3 translational modes. Each one of them has kb over 2 times temperature as the energy. So the translational kinetic energy of this molecule would be 3 times kb over 2 times temperature. If you know the temperature, you can calculate the kinetic energy of that one molecule as it moves. Then you could also set that equal to 1/2 mv squared and solve for the actual speed of the molecule if you know its mass. Any other questions on that? All right, try applying those ideas to the questions in the FNT to get some practice, and I will see you next time.
Thank you.
You're welcome.